All the Python source code for this lesson is available for download. See video description. Welcome to our journey into the fascinating world of artificial intelligence. Today, we're going to uncover how a neuron functions in AI through a series of illustrative diagrams and animations. Our adventure begins with a line of 4 circles representing our input data, denoted as x1, x2, x3, xn. These inputs are the raw data that we feed into our neural network. They could be anything: pixels in an image, words in a text, measurements from a sensor, and so on. As we move to the second line, we encounter the learnable weights: W1, W2, W3, Wn. These are the variables that the neuron will learn. These weights determine how much each input contributes to the output of the neuron. In the third line, we find the sum of the products between each input and its respective weight. This operation is at the heart of our neural network. Each input is multiplied by its weight, and the results are all added together. This is sometimes called the weighted sum. In the next line, we add a special term called a bias. The bias allows us to shift the neuron's output up or down, giving us more flexibility in fitting our model to the data. Now, we reach the activation function. We've depicted several popular choices here: softmax, ReLU, leaky ReLU, sigmoid, and tanh. The activation function takes the weighted sum and transforms it, often in a nonlinear way. This transformation is what allows neural networks to model complex patterns. Finally, the last circle represents the output of our neuron. This is the result of the AI's prediction, based on the inputs, weights, and activation function. Connecting all of these elements are lines, suggesting the flow of computation. Downward lines represent the forward pass of data through the network. And upward lines with the letter B represent backpropagation, where the network learns from its errors. On the right, we have an animation that cycles through 370 epochs, showing the process of computation and backpropagation in action. Throughout the animation, we pause to examine charts of the tanh function, the bias, the sum of products x1 * w1, and the evolving weights and their corresponding gradients. Through this visualization, we gain a deeper understanding of the inner workings of a neural network. From the raw inputs to the calculated output, we see how data is transformed, how weights are adjusted through learning, and how backpropagation allows the network to learn from its mistakes. By the end of this journey, you'll have a solid grasp of key AI concepts like neurons, convolutional neural networks, CNNs, derivatives, and backpropagation. And hopefully, you'll see that these concepts, while complex, can be understood and visualized in a clear and engaging way. The simulation was done using the Python library Micrograd. Micrograd is a tiny autograd engine and a neural net library on top of it with a PyTorch-like API. It was created by Andrei Karpathy, and it is designed to be a simple and educational tool for understanding how deep learning works, to understand how these systems work at a lower level. Micrograd is very small, with only about 100 lines of code for the engine and 50 lines of code for the neural net library. This makes it a great tool for learning about the basics of autograd and neural networks. Micrograd is also very easy to use. The API is similar to PyTorch, so if you are already familiar with PyTorch, you should be able to pick up Micrograd quickly. Autograd. Autograd is a Python library that provides automatic differentiation, a technique used for computing derivatives of functions. It is a crucial component of many machine learning algorithms, particularly those used in training deep learning models. Here's a bit more detail. Automatic differentiation. This is a set of techniques to numerically evaluate the derivative of a function specified by a computer program. Automatic differentiation breaks down a complex function into basic operations, like addition and multiplication, for which derivatives are known, and then applies the chain rule to compute the derivative of the entire function. Use in machine learning. Many machine learning algorithms involve optimization. For example, when training a neural network, the goal is often to minimize a loss function. This process requires computing gradients, or derivatives of the loss function. AutoGrad can automatically compute these gradients, which makes it easier to implement and experiment with new machine learning models. Compared to symbolic differentiation and numerical differentiation, automatic differentiation is different from, but related to, symbolic differentiation and numerical differentiation. Symbolic differentiation can give exact derivatives, but can be slow, and not all functions can be symbolically differentiated. Numerical differentiation is fast, but can be inaccurate due to numerical approximation errors. Automatic differentiation can be thought of as a balance between these two. It is as fast as numerical differentiation and as accurate as symbolic differentiation. AutoGrad can compute derivatives of both scalar and tensor functions, and can also handle functions with any number of inputs and outputs. This makes it particularly well suited for use in deep learning, where models can have millions of parameters and be used on high-dimensional input data. Activation functions. Activation functions are a crucial component of neural networks. They determine the output of a neural network, its accuracy, and also the computational efficiency of training and inference. Here are some commonly used activation functions. 1. Sigmoid function. The sigmoid function takes a real-valued input and squashes it to range between 0 and 1. Sigmoid functions are often used in the output layer of a binary classification problem where the goal is to predict something that can take on two values. 2. Tanh function. The hyperbolic tangent function is similar to the sigmoid function but squashes the input to the range between -1 and 1. It is often used in the hidden layers of a neural network. 3. ReLU. Rectified linear unit function. The ReLU function outputs the input directly if it is positive, else it outputs 0. It has become the default activation function for many types of neural networks because a model that uses it is easier to train and often achieves better performance. 4. Leaky ReLU function. Leaky ReLU is a variant of ReLU that solves the dying ReLU problem, where a neuron can sometimes be stuck in the negative phase and always output the same value. Instead of defining the function as 0 when x less than 0, we define it as a small linear component of x. 5. Softmax function. The softmax function is often used in the output layer of a classifier, where we trying to assign the input to one of several classes. Unlike the other activation functions, softmax outputs a vector that represents the probability distribution of a list of potential outcomes. Each of these activation functions has its pros and cons, and the choice of which to use often depends on the specifics of the problem at hand.